Hello, I recently bought one of these Asus Xonar U7 Mark II USB sound cards. So it's got fairly decent specification with a maximum sample rate of 192 kilohertz and up to 24-bit sample bit depth, and advertised 114 dB signal to noise ratio. So that looks pretty good. Look at some more specifications here. So the 114 dB is on the output signal to noise, and it's actually A weighted. Still quite impressive. On the input we get 110 dB signal to noise ratio, and the output total harmonic distortion plus noise at 1 kilohertz is specified as 0.0006% or 104 dB down. Very impressive. And the frequency response all the way down from 10 Hz to 46 kilohertz within 3 dB. That looks pretty good. The output voltage, it's a little bit limited, 1 volt RMS on the line output, and the headphone 1.3 volt RMS. But overall, this looks very impressive. So these sound cards sells for around $70 to $80 US, so fairly reasonable. So the reason I bought this sound card is because I've been working on adding support for regular Windows sound cards in my audio analyzer software. However, once I started doing some measurements, I didn't find the performance to be quite as impressive as the specifications would indicate. So what we have here is a GHD plus noise measurement, just taking the output directly into the input on the USB sound card, and it's from 20 Hz to 20 kilohertz we have here. It starts out quite nice. It's very good up to about, 300 Hertz. Then the distortion just starts rising and rising and rising all the way up to 20 kilohertz. I think we're at 0.03%. So clearly something is not quite right. So I thought, well, let's have a closer look at see what's going on with the sound card. So when we take the top off here and take a look at the circuit board, we can see here's the USB input. This is a digital output, and then we have the surround channels over here, the two main left and right over here, and here we have a headphone output, and we have the input. So this is a combined line input and a microphone input. We take a closer look at the circuit here. What we have over here is clearly the power supply section. So we have some kind of small switch mode controller here. It looks like one of the Texas Instrument parts. This most likely generates a constant 5 volt output. These little things, they switch at a very high frequency, something like 1 megahertz, and we can see here the inductor is quite small value, just 2.2 microhenry, and we have a few capacitors here. And if we go over here, so this is the main sound card controller. It basically does everything you need in a sound card, this chipset here, and it's a CM6632. It even comes with a built-in microcontroller. It's got I/O ports, and you can program it and all sorts of things. And it basically does everything digital. Does the USB. It generates all the clocks for the DA and AD converters. You can see we've got a number of crystals over here. And moving over, what we have here is a multi-channel 6-channel DA converter, and that is for the surround outputs. And what we have over here is all the coupling capacitors, because everything is powered by 5 volts. So to get rid of the 2.5 volt DC, they use coupling capacitors here, and you can see we've got the outputs here, rear output, center, side, and I think it's got the subwoofer here as well. Moving over further, so what we have here is, so they do have a volume controls, just an encoder, nothing special there. And here we have the main DA converter. It's quite a decent Cirrus logic. Both the DA converters here are Cirrus logic, and I believe there's some op amps on the back side. We can take a look at that, and it's got some relays to enable, disable the output, probably to avoid any spikes on the output when you switch it on. And if we move down here, what we have here is the front end for the input. Have a couple of op amps here and a lot of capacitors. So looking at the back side here, we still have a lot of components. If we start over here, what we have here is the op amp for the main output with a few capacitors and filtering there. And over here, these 3 op amps we have here are for the surround outputs. And over here, what we have is the analog to digital converter. It's also a Cirrus logic. And then we have some memory here, some sample memory for the main sound card controller, because, well, USB is not exactly a streaming protocol. It's packet based, so you need some memory to keep all the samples both coming in and out. Other than that, there's not really anything exciting on the backside. There's some protection stuff, but not that exciting. Okay, so now we know the components being used, at least the analog to digital converter and the digital to analog converters. They're all very high quality, including the op amps, good stuff. So where's the distortion coming from? My best guess is that it is part of the input stage. The front end we look at here, so it looks like they are using ceramic capacitors for coupling, and, well, it's all ceramic capacitors here, right, instead of electrolytic and film capacitors. So I think it's worth trying to bypass this front end and just go directly into the analog to digital converter and see if that improves the performance. So if we take a look at the data sheet for the analog to digital converter, you can see it's quite nice specs we have here. 114 dB dynamic range, 105 dB total harmonic distortion plus noise. And if we look further down, there's a reference design for the analog front end for the input for the AD converter, and we can see we've got with a couple of op amps here, some filters and stuff. And one thing worth noticing is the reference center voltage, so it's going to be swinging around about 2.5 volts, but that voltage comes from the AD converter, so it will provide this reference voltage. So what we have here is, right, the signals are going to come in, a balanced signal here. It's going to swing around 0 volts, and then we have a coupling capacitor here, and then we change it to swinging around 2.5 volts, so half the supply voltage of the op amps and the AD converter, and various filters. So I think I would like to try build a new front end, something very similar to this, and let's see if that improves the performance. So what we have here is the schematic for my redesigned front end. So the signal comes in here. So we want to have a balanced input. So it's going to be a positive and a negative input and a ground. And then we have some attenuation. And I've added some diodes here for input protection. So these are going to be some ultra fast, low leakage diodes, coupling capacitors here. And then we have a reference to our center voltage. And this box here, this is just a dual op amp. It was just the only footprint I just quickly could find. And basically this whole part here is exactly the same as what we had in the data sheet. And here we have the circuit board layout. So it's a very simple 2-layer board. And here I've milled the circuit board for our new input stage. And here we have the top side of the board and left and the right input. And notice I'm using electrolytic capacitors for the coupling capacitors. So these are bipolar capacitors. And for the filter, I'm using film capacitors. And a quick look at the bottom side here. So the inputs are over here. and we have our attenuation resistors and stuff here, the op amps, and the only other capacitors I have on here are a couple of power supply decoupling capacitors. So I need to try hook this up and see if it improves performance. So to hook up the new front end, we need to make a few small modifications to the circuit board. So I would like all modifications to be reversible, because I don't know if this change is going to have any effect. Maybe it will make the performance worse. So then I would like to return it to original. So what I have marked here in red is all the components that have to be removed in order to completely disconnect the original front end from the analog to digital converter. And then we can connect in the new front end using these points I marked here. So this is the center voltage reference. It's on both these two pads here. And the right side in negative is on the top pad here. Right side positive, the bottom pad left in negative, the top pad left in positive, the bottom pad up where this capacitor that's been removed was. And to get the 5-volt supply voltage, we can just take it across one of these power supply decoupling capacitors. Here is plus 5 volt up here, and is a ground down here. Okay, time for the moment of truth. See if this actually makes any improvement to the performance. So the new front end has been soldered in to the original board here, and I connected the line out to the new board here. So this is of course single-ended, and this is a balanced input. So the negative part of the positive negative is just connected to ground, and then the signal here is just connected to positive. However, I noticed there was a small quirk. The sound card got some kind of detection whether there's anything connected on the input here. So it will not actually enable the input unless there's something connected here. So it's probably just 2 pins that need to be shorted somewhere, and then we don't need to do it. So I'll just connect a cable here to cheat the detection, and ready for the first distortion measurement. And here we have the distortion measurement with the new front end, and it looks much better. You see, it's much lower distortion. We don't have, before we had this rise from around 200 to 300 hertz where it would just start rising the distortion. We don't have that anymore. There's a little bit of bump up here, but that's nothing. It's looking pretty good. And here I tried overlaying the new distortion measurement on top of the old measurement. So you can see it is significantly better. This might not look like much, but this is a significant improvement in the performance. The noise floor might be a little bit higher because, well, I'm not using any shielded cables or anything like that, so I could probably improve that even further by using some shielded wires. But as a proof of concept, this is a big success. So to take it even further, I think I would like to make some kind of front end where I can adjust the attenuation. So anything from line input up to if you connect a 250 watt amplifier, it would be able to take those voltages. I might also have a look at the output, because it is somewhat limited with only 1 volt RMS output. It would be nice to at least have 2 volt RMS. I might have a look and see if it's possible to do something, but that's going to be a future modification. This was more proof of concept, and I'm happy my guess was correct, that it was part of the input stage. So thanks for watching, and I'll see you next time. Bye bye.